Recrystallization, performing the technique. In this webcast, you will discuss the thought process behind performing a recrystallization. Depending on what kinds of impurities are present in your compound, you will utilize different techniques. Mechanically, a recrystallization is quite simple. You take your impure solid and you dissolve it in an appropriate hot solvent, using as little volume of the solvent as possible. We'll talk about what an appropriate solvent is shortly. Once you have dissolved your impure solid in as little hot solvent as possible, you then allow that solution to slowly cool. As the solution slowly cools, the solubility of your solid will decrease, and if you have performed the technique properly, result in crystals of your compound to begin to form. These crystals should be pure because the impurities should be left behind in solution. Now, this assumes that your impurities are soluble in the solution. In the event that you have insoluble impurities, you have to perform what's called a hot filtration. We will talk about soluble impurities and insoluble impurities shortly. But first, let's talk about solvent choice. On the previous slide, I said you had to use an appropriate solvent. There are a few criteria a solvent must meet in order to be useful in a recrystallization. First, the solvent cannot react with the compound. It must be what we call inert. Remember, in a recrystallization, no chemical reaction should occur. Second, your solvent should dissolve all of your compound when it is hot. It also must dissolve as little as your compound as possible when it is cold. Let us look at this graph on the right. If you look at the line for sugar, we see that as our temperature increases, as our solvent, in this case water, gets hot, we dissolve a great amount of sugar. When we allow the water to cool back to roughly room temperature, we see that the solubility has decreased dramatically, meaning that most of our sugar should return to the solid phase. Therefore, water could be used to recrystallize sugar. In contrast, if you look at sodium chloride, this bottom line, we see that the solubility does not change very much as our temperature increases. Therefore, water would be a poor solvent to try and recrystallize sodium chloride from. Finally, as a practical concern, our solvent should be volatile. In other words, easy to evaporate, easy to remove. The easier it is to dry your crystals, the better the recrystallization. Earlier, I mentioned insoluble impurities and soluble impurities. Insoluble impurities are impurities that do not dissolve in the solvent, even when the solvent is hot. As a result, these must be filtered out. We'll talk about how to do this shortly. Here on the right, we see a test tube containing a solution of some kind, and in this solution is suspended some solid. Because this solid will not dissolve in the solvent, this is an insoluble impurity. A soluble impurity is an impurity that dissolves in the hot solvent and is still dissolved when the solvent is cold. Here on the right, we see a test tube containing a solution that clearly has no solid in it. In other words, everything in here is dissolved, is soluble. Finally, you can have partially soluble impurities. These partially soluble impurities are a sort of middle ground between soluble and insoluble. Because of this, they are often difficult to remove. For this course, you should concern yourself primarily with insoluble impurities and soluble impurities. Let's say we have a sample of a solid that contains both an insoluble impurity and a soluble impurity. What do we do in order to purify our solid? The first thing we do is remove the insoluble impurity through a hot filtration. When removing an insoluble impurity, you attempt to dissolve all of your sample in hot solvent. What will happen is your desired compound will dissolve, as well as any soluble impurities. The insoluble impurity, however, because it is insoluble, will not dissolve and will remain a solid. You will then perform a hot filtration. In this lab experiment, you will use gravity filtration to remove the insoluble impurity. In the image on the right, we see an example of a hot filtration. We have an Erlenmeyer flask containing a hot solution with an insoluble impurity, and we are carefully pouring that hot solution through some filter paper. The solvent will pass through the filter paper and be collected in some collection vessel, while the insoluble impurity will remain behind, caught by the filter paper. When performing a hot filtration, you do have to take care. The moment you take your flask off of the hot plate, your solution will begin to cool. If it cools too much, your desired compound will begin to form crystals, and those crystals will be caught in the filter paper. A hot filtration must be performed rapidly, but also carefully. The glass will be hot and the solution will be hot. To slow the rate of cooling that will occur as your solution passes through the filter paper, you can pre-warm the filter paper and the funnel using pure hot solvent. Okay, so we have now successfully removed our insoluble impurity. Excellent. But we still have this soluble impurity to take care of. How do we do that? Now, we perform a recrystallization. When performing a recrystallization, you have an impure solid that you will dissolve in an appropriate, and we discussed what appropriate means previously, hot solvent using as little volume as possible. Of course, as little volume as possible is not particularly specific. When you begin a recrystallization, how much volume of solvent do you use? A good rule of thumb is to add enough solvent to cover your impure sample. You then boil that solvent and try to dissolve your sample inside of it by swirling the container. If swirling the container and boiling the solvent is not enough to dissolve all of your sample, that's when you begin adding small amounts of more solvent. You continue this process until your entire sample dissolves after swirling and boiling solvent. As you can see here, in this image in the bottom left, we have a solution of an impure solid which has been dissolved in boiling solvent. You then allow your solution to slowly cool, and as the solubility decreases, crystals will begin to form. Taking this solution on the left and allowing it to cool forms these crystals you see on the right. The yellow impurity that was present remains in solution, while the solid crystals that formed are now pure. In this experiment, to collect the crystals you will form, you will use what is called a vacuum filtration. Let's say you were performing a recrystallization, you've done everything properly, but crystals just won't form. Why might this happen? Ideally, when you make a supersaturated solution, the solute should immediately leave the solution and form crystals. Occasionally, something called metastability is reached, where the solute refuses to return to the solid phase and form crystals. To try and encourage crystal formation, or what we call induce crystallization, you can take a few actions. The first is to cool in ice. Once you put your solution in ice, you should then be patient. Your solution will not cool instantaneously. If you have waited an appropriate amount of time, 5 or 10 minutes, you can then try to induce crystallization by scratching the inside of your flask with a spatula. By scratching the glass on the inside, you make a rough area. The rough area provides a place for crystals to begin growing. If you have taken all of these actions and crystals still won't grow, then it is very likely you have used too much solvent. If you have used too much solvent, all of your compound may be soluble in the cold solvent. To try and fix this, you should concentrate your solution. To do this, you should evaporate some of your solvent. To prevent this situation from happening, when dissolving your impure solid in hot solvent, make sure you are using small volumes of hot solvent to begin with thorough swirling. To recap how to perform a recrystallization, here is a flowchart. First thing you ask yourself is, when given a sample, is your compound pure? If it's pure, then you're done. There's no need to perform a recrystallization. Of course, we are not going to give you a pure compound. So, let's say your compound is impure. What do? You dissolve your sample in hot solvent. You then look at your solution. Are insoluble impurities present? Do you see solid still? If yes, then you perform a hot filtration to remove those insoluble impurities. You then take the solution that passed through and allow it to cool and form crystals. If there weren't any insoluble impurities, then there is no need to perform a hot filtration, and you go straight to allowing your solution to cool to form crystals. Then you look at your solution and ask yourself, okay, are crystals being formed? If not, then you have to induce crystallization, either by cooling the solution, being patient, or scratching the inside of the flask. If you used too much solvent, you may have to concentrate your solution by boiling off some solvent. Once crystals begin to form, you then collect your crystals via filtration. In this case, you will be using vacuum filtration. If crystals formed without any induction, then you simply filter them to collect them, and then you will determine their purity. If your compound is pure, then you are done. If your compound is still impure, then you go through this process again and repeat until your compound is pure. That brings us to the end of this webcast. To recap, the solvent used in the recrystallization is crucial to success. Your solvent must dissolve the entirety of your sample when hot and as little as possible when cold. The type of impurity or impurities present within your sample determines what procedures to perform. An insoluble impurity is removed through the use of a hot filtration. A soluble impurity is removed through a traditional recrystallization. To ensure sufficient crystal formation, you should use as little solvent as possible to dissolve the entirety of your compound when it's hot, and then carefully chill your solution as much as possible in order to minimize the solubility of your compound in the solvent.